Welcome all to this webinar about advanced parameters and how we're going to use them to optimize and troubleshoot hydraulic model. Here is a quick agenda to show you what we'll cover during this webinar. It is quite technical, so we'll bring a bit of context on the modeling process and the flood modeler solving process prior to discuss key advanced parameter in flood modelers that can be classified for the purpose of this webinars as you can see here, iteration parameters, numerical solution parameters, and also I'll cover some of the other parameters. It's quite important to flag at this stage that I won't cover during this call all the flood modeler advanced parameters because it's quite a big list, but I will focus on key ones that are useful and influential to help troubleshoot and optimize hydraulic model. We'll finish the session by a summary and 10 minutes of Q&A. So, first of all, so a quick reminder that with the recent versions of flood modelers, the advanced parameter tab in the IEF file, as you can see here, is hidden by default. So just a reminder for you you will need to go to activate it via the tabs menu shown here. The advanced parameter I'm going to cover today are the one literally located to the left, being defload, stall, qtol, meter, max heater, theta, and alpha. As I said, at the end of the session, I would briefly discuss some of the other. To bring further context to our discussion, let's remind ourselves about the modeling process as laid out on this slide. Starting from real world of a particular river system, for example, we are aware that there are physical equations that describes the hydraulics of a river in general, and the modeler do schematize, stroke simplify the river system into a model using flood modeler software. So software then mathematically solve the physical equation via the processes of linearization and discretization of the mathematical equation, and it ends up by providing a numerical solution being expressed as stage and flow at every time step previously set up by the user, and model node or cross-section of the model river system during a given simulation of an event, being a flood event. The result of this project ends up with some model outputs that can be shown by the model user and share with his client. So that in that context being introduced, I need also to move on to another aspect of flood modeler, which is the solution process. So flood modeler, in terms of the solver, solves the mathematical equation, which are usually known as shallow water equation, where they are reduced to 2 dimensions, and Sandvenant equations when they are reduced to 1 dimension. And they do so using a partially implicit method known as Pressman box scheme. So what is the implicit method? Well, it's essentially using the results at the current time step to calculate a numerical solution at this time step. That sounds like an oxymoron, but in reality, as depicted on the flow chart to the right to reach to a numerical solution. You need, for a given time step, you need first to make a guess, okay, and solve the equation we are talking about. So in the case of 1D, the 7 equation, iteratively, so through some iteration which are depicted here, there is some a form of a loop system. And when the iteration process is completed, then you move a time step forward, and basically the solution that used to be at the previous time step become the initial solution for the next set of iteration. Okay. Of note, the very first guess before the first time step are the initial condition that, as we all know, so in the dat file or the init files that Floodmodeler requires before the start of any solution. And then each subsequent zeros iteration guess is, as I said before, the previous time step solution. So having introduced those two, the model process and the Floodmodeler solution process as a context, I can move on to discuss in the first place what we call iteration parameters. Okay, and those are, as you can see on the left-hand side, edge toll and Q toll, min-iter and max-iter, and ev-iter. And why we call them iteration parameters is because they have a direct influence on the iteration process described previously, which is at the heart of the Pressman's box of Minsky. So let me define what they are first, and then I'll show you why one would change them to optimize or troubleshoot Floodmodeler algebraic model. So edge toll and Q toll are numerical tolerance valued. There are differences in stage and flow which must not be exceeded at each model node between iteration. If exceeded after reaching the maximum number of allowed iteration, which is defined by max-iter here, a poor convergence warning is issued by the software. Edge toll, which relates to the calculated stage, is an absolute value, and its default, as we all know, is 10 millimeters, so 0.1 meter. Whilst Q toll, which is related to flow, is a related value which is expressed as a percentage unless the mean flow is strictly lower than 1 cubic meter per second, in which case Q toll is an absolute value. The next sets of iteration parameters is max-iter and min-iter. They, in essence, control the minimum number of allowed iteration. Max-iter obviously must be larger or equal than min-iter, and min-iter at least needs to be equal to. Note that the default value are respectively 11 for max-iter and 3 for min-iter. Finally, another couple of two iteration parameters are AVTR and nSpint, and those two are used in adaptive time step heap only. They control when the solution is allowed to increase time step. if the solution converges within an average iteration over S being successive time steps during then a doubling of the time step is attempted by flood modeler. And please note that FVTR should be larger or equal than miniature. Okay, so that is a brief description of what are those iteration parameters. Now, let's see, coming back to this demo, okay, why and why not and when one would change this to optimize or troubleshoot your hydraulic model in Flood Modeler. So for HTOL and QTOL, as we know, those are what we call tolerance parameters. So they determine how good the numerical solution needs to be before considered as solved. The smaller the number, the tighter the tolerance. If these parameters are increased from their respective default, which is, as we've seen before, 0.01, then generally the less accurate the solution is, which may manifest itself as mass error. However, decrease them and the solution may take much more time to converge or not converge at all. Okay, so usually the default value are considered as sufficient, and we would not recommend to change them. And if you were to change them for troubleshooting purpose, we strongly recommend that when troubleshooting is completed, you put it back to their default value. With regard to max iter, okay, one would increase it to give the solution the opportunity to converge, and it's quite often the case with very complex models that we do increase max iter. So it is advised as well that you use a prime number. The recommended value is 11, and you can increase this value for, again, giving the solution more opportunity to converge to probably what would be recommended is not to exceed 30. So the next prime number would be 29. For miniature, which is here, essentially the reason why you would increase miniature is to reduce some mass balance error and dilute as well some negative effect associated with the change of alpha, which is, you will understand in the next slide also when I'm going to talk alpha, why miniature can counteract some adverse effect associated with changing alpha. Now, having miniature too high and the solution will obviously takes longer to run. So with recommended value is currently 3, and you could go with having 4, but I wouldn't recommend to exceed that number. Finally, for eviter, as I said before, it must be greater or equal than mediator, and again, it's only affects the adaptive time stepping, so it's quite, you've got quite different reasons why you wouldn't change that one. But if you, because as I say, it's an attempt to tell Flumler to double the time step. So if you are not satisfied, you could potentially increase it up to miniature +1. Now, if you got some issues with troubleshooting and your model crashing, please consider switching back to a fixed time step where you've got this detailed iteration and more control on the time step in essence. Okay, so I'm going to move to the next set of parameters, which is the numerical solution parameters, which are theta and alpha. Again, quick definition of what they are. So theta controls the degree of implicitness of the numerical solution. So remember in the previous slide, we were talking about the Pressman slot and say it's partially implicit, where it is the case because actually by default theta, which controls the degree of implicitness, is 0.7 and not 0.1, which would be, in the case of 0.1, would be a fully implicit. And 0 would mean that the solving scheme is explicit and this is not allowed by flood modeler. So the minimum allowed value is 0.5. Theta is effectively a temporal weighting towards a solution between the numerical solution being between it's a weighting factor because you are influencing the current solution with calculated at the given time step with the solution calculated at the previous time step. Whilst alpha, okay, also known as an under relaxation parameter, this is a parameter which weights the calculated solution as with a certain proportion, 1 minus alpha, towards previous solution calculated during the iteration process. So effectively, what it says is you, or at least the solver does, go to the trouble of calculating a solution, but you don't use it 100%, and you need to take a proportion of the previously calculated solution, and we'll say previously it was at the previous iteration. The value here indicated either could be the calculated head or flow, okay? And again, the value, you can see the value from the previous iteration is also alphaized, hence increase dilution with increased iteration. So this is where what I'm trying to say here is because you are using partially the previous iteration, there is a changing alpha inherently introduce some mass conservative error. Okay, and as said previously, to counteract this effect, you can increase the minimum number of iteration so that you don't, having changing alpha, you don't have too much of mass balance issue. Okay. Now, the practical effect of changing alpha is really, it helps smooth the solution between iteration and reduces the change effect of sudden spikes and give more a chance of obtaining a valid solution. Okay. So again, why would we change theta? I mentioned before, we'll change theta to have something, increase theta towards 1, to have something a bit more implicit, which is allegedly known to be a bit more stable. Now consider that increasing it as well to improve stability. but it will be at the expense of solving speed. So most of the time, it needs to be a compromise between what you want to achieve and also the time it takes for the new model to run. Equally, as mentioned, we will decrease alpha to help during the iteration process and smooth the transition and void instability and spike in a poor conversion spike. But again, that can have, as we said, some impact on mass balance and also on the time it takes for the model to run. Okay, so a quick, just about time, but a quick coverage of other advanced parameters. The most well-known to modelers is defload, and as you know, defload is the height in meter of vertical walls are added to the ice ponds on each river cross-section to allow for flooding. Default value is 3 meter and is quite often increased on link 1D to D link model to allow the computation to happen, particularly when between the 1D and 2D there's lots of water ponding on the 1D 2D link, so above 3 meter. It's also known to overcome some temporary instabilities. Again, if you were to increase defload for non-linked model, please be mindful that it's artificially increased and it will affect your conveyance calc. Another set of other advanced parameters that can be mentioned here, weights. Weights is nothing else than alpha for spills. Okay, so you could tweak it to 0.1. Its default is 0.1, but again, it has to be a compromise with the accuracies and be mindful of mass conservation. There is another parameter called the orifice lineation head, which you might want to tweak if you got some instabilities associated with level on either side or an orifice unit being very close to each other. It's expressed in meter and recommended value if you got issues with stability is 0.1. Finally, you've got PS deep and PS wide, which control the pressment slot if you have this option activated, and that controls the dimension of the pressment slots. And one reason that you would tweak them is probably to offer a bit more stability at low flow, because you would increase the pressment slot. Now, do that and be mindful to keep the pressment slot in proportion to your model dimension, because in essence, it's introducing some artificial area in your cross section. So, to recap on this webinar, and it's been really just an introduction on why we would change some key advanced parameter, essentially for troubleshooting and computation optimization. Default value should generally be used, and if you were to make some changes and use that for your client when typically when you hand over your model, justification for the changes should always be provided. That's a strong recommendation. And as is what mentioned at the beginning of the course, there is a flood modeler to the course for advanced parameters, where I'm actually giving that score where we further explore the topic of using advanced parameter for troubleshooting. I definitely recommend this course to be attended. It's a 2-day training course, and that gives us really enough time to delve into this topic, which I acknowledge is quite technical, and hopefully um, during this very short webinar that gave you um, you know a bit of what it is to deal with and tweak advanced parameter.